we have another presentation from Taiwan, Wei Chin-Chung.
Thank you, Chairman. And my presentation is for the study of the wear effect and the preload decay affects the fraction and the content behavior of the. Sorry, this cut is for the post school. And as we know, the post school is widely used in the tool machine, and it's a mean preference is the preload is decayed with the operating distance. So it will affect the positioning accuracy and the structural stiffness. So we are concerned in what the wear affects the context and the fraction and for the transmission. And the post school is applied in the vertical transmission is very widely used in the industry and for the fabrications of like the iPhone's cage. And the global world, 80% are produced by the Fanaco. It's a Japanese company for this kind of machine tool. And the high-speed transmissions is will bring the wear and the thermal effects. But about the transmission mechanism analysis in both school is very few. So especially for the preload effect, fraction, lubrication, wear, and the fatigue analysis. Most preload applied in the both school have these two types. The first one is called the offset preload. Is you can see here the each ball only 2 contact points, and the other kind is the oversized preload. It's each one ball have 4 contact points, and this kind will increase the stiff contact stiffness of the ball contact mechanism. In the research is mainly in the offset type. And while we test both school in the vertical transmission, we can find the preload is decayed with the operating cycles. But we also find the transmission torque is non-steady. While the preload torque decrease under the 30%, so the variation will be large. But the transmission torque is the average transmission torque is remain. And we also measuring the saturation frequency of the ball is also remain. So we very we have interesting in what problems in the transmission mechanism. So this is the cross section of a ball school. You can saw the balls is many turns in a ball school. And the actual load applied here, and the preload is applied in the ball school. And in 203, we create the single ball models and considering the centrifugal force and the contact angle. And 209, we also create the double raceway and the preload effect. and considering the lubrication. So, but we find many times for school is the multi-cycles. So the problem is the force participation is a problem because even though the two cycle force is many equations, many equations. So if multi-cycles is more equations, it can easy to analyze. And the other problems is the preload decay is how to affect the transmission performance. So the four turns four model is like this. It's applied the upset type preload. And we also do some assumptions is steady state conditions. Not is only suffers the actual load, and each turns just one ball on the raceway. Centrifugal force is considered in the model, and the lubrication condition is EHL, but we also considering the wear effect on the model. And while non-actual load applied, the model is like this, and here is the preload. But when the actual load applied, the contact behavior will be variations at each point. And first, we are thinking how to do the force participation. And if you separate these two parts, we can solve it's just the two-pole condition. And we also have the original two-pole transmission analyzed model. So we think we just need to partition the force to each side. We can calculation the models. And the flow chart is like this. And we use the force equivalence on the nuts and to calculation the actual load at each side, and then find out the total solutions. And this is the total flow chart for the 4 cycles for school model. And in here, the conditions is the content angles and the force equivalence, and to find out the all solutions. And we also measuring the vibrations at the nut, and to find out the recirculations frequency of the ball, and we can find the conditions is very nice between the experiment and the analytical. And we also can find each sliding speed at each contact side. And the stiffness also can be obtained by the commercial equations listed in the tables. And in our situation is the fixed free support type. And the transmission torque, we also can find out for the school is driving torque. And you can solve the conditions, the equations is mini in contact force and the friction force to generation the transmission torque. And we also can find out the nut torque. And because we can measuring the preload torque under a very low rotational speed, but the measuring is from the nut, so we also can calculate the preload torque from the nut. And the raceways geometry is like this, and we can show the roughness on the raceway is have the specified directions. Sorry, have the specified directions. And on the spool is not so large, but on the nuts is more rough. We also using the two-body contact theory and to create the wheel models. And this is shows the equations for the wheel rate is consisted with the effective contact ratio and the wheel frequency and the wheel depth of rock tip. And because the both roughness is more smoother, so we considering is the composite roughness on the raceway, and this is shows a single the roughness peg, and the before the contact is like this geometry, and after the contact is the second geometry like this. So we can find out the how many percentage of the plastic contact, and the assumption is all removed. So we can find out the areas volume like this. And the variations of the preload is can be find out from the wear depth, and we also have the contact stiffness, so we can find out the how many preload exist on the contact area. Okay, and this equations shows the wear rate. Wear rate is consistent with the effector contact ratio, wear frequency, and the wear depth of the rock peg. And this is the flow chart of the wear model. Okay, and we can show the results shows at the left contact side is these conditions. Is decreased with the actual load, but the right side is increased with the actual load. And the relative speed between the contact surface is increasing with the rotational speed, but it's not affected by, it's very few with the increasing of the actual load. And the wear frequency is increasing with the sliding speed. So you can show the left contact side is have a larger wear frequency. And this figure shows the wear depth of the single tip. And it's the plastic contact ratio is shown here. And we also considering the elliptic ratio. Elliptic ratio is the semi-short axis to the semi-long axis. And this means the geometry of the roughness peak effect. So in this figure, we can show is the wear depth of the spirity of the spirity is in at the left side is decreased because the contact force is also decreased with the actual load increasing, but the right side is increased with the actual load. And this figure shows the wear rate. Wear rate is also is increasing with the actual load. It's like this. And this figure shows the actual wear depth, and you can see is also reflected to the preload. It's decreasing with the stroke number. The decreasing rate is increased with the operating speed. Okay, and this line shows the minus 10% of preload is decreased. The preload 10% is this line. Okay, and this figure shows the elliptic ratios effect, and we can, so if the elliptic ratio increasing, the decreasing rate of the preload will also decrease. You can see if the peak, the ratio is smaller, the decreasing rate is larger. So it means if we can control the surface is like that, the roughness peg is similar to the surround shape. It's more appreciate approaching the surround shape. The whale can be reduced, and this is our experiment set up like this. Due to the time, so I will increase, and you can see the actual load increase. The right left both will changing the contact directions, and we also convert with the strength surface strength of nuts. You can see the analytical results, and the experiment is well fit. So we test this, and sorry, and the mean for the preload effect, you can see the contact while the preload increasing the contact force, left contact side is reduced, but the left side is increased. So while we calculation the transmission torque, we can find the left side reduced, but the left right side is increased with the preload. So, but the torque of the nuts is also increased. So the summation these two is the total transmission torque of the both spool, and we can find is remain as the constant. So it's also reflected to the experiment. We also have the study for the oversized ball, but this is just started the study, and we can find the preload reducing speed of single nut ball is larger than the double nut. I think it's due to the single nut ball is oversized ball, but it's the both numbers is just half of the double nut. Okay. So finally our conclusions. Well, frequency increases with the rising of the rotational speed, and the ball nut is always higher than the ball spool due to more slipping motion occur at the contact area. And the wear depth of the and stability is the major vary with the dimensionless contact force and the plastic contact ratio. Axial wear depth and the decrease of the preload are reduced with the rising of the elliptic ratios. So the elliptic ratios is the surface design mean factors of a both raceway. And the study also provides the new concept for the force partition for the multi-cycle force school. And the relationship between the transmitting torque and the preload decay is created. And our corporations is the Highwind Technology, is the Taiwanese company. And we also have for the international conference, Aztec. Welcome everyone to join us. And this is the list of the we hold the conference each year. Thank you for your attention.
Thank you very much for your presentation. And now we have time for one or two questions.
Thank you very much for very interesting results and presentation. And my question is, what kind of contact condition did you use in individual contact spot? Did you take into account stick-slip phenomena, which takes place when there is rotation, rolling contact? So please explain what particular your contact condition within inside the individual contact spot.
Okay, is in the 209 we also we have a 2-10 model, and we calculating the model the contact conditions with the force equations and the kinetic equations. So it's this 4-10 models is based on the 2-10 model, and we the problem is how to separate the actual load to the two sides of the both school, two sides of the both school. So we find is each side have the 2 4-10s. So we use the force equivalent on the nut, and to separate it, and it's converged for the iterations, and to find out the actual force on the nut at each side. I don't know. The explain has explain your questions.
No, my question is not about force. Yes, I understand your assumption about forces, but due to existence of force, we have the contact area, and inside the contact to calculate the shear stress, we must assume that there is a stick and slip zones inside the contact area. If you took into account this this effect, the particular conditions for shear stress within the contact area.
Contact areas, and but excuse me, I don't understand.
So due to forces applied to the contact, we have the contact area, but in rolling process, the contact
you mean the contact situation on the contact area?
Yes.
The Hodgkin contact.
Stick and slip phenomena. So there is rolling contact. So there are stick and slip zones inside the contact area. And for example, friction coefficient influence on their dislocation of the zones and their size, and also influence on shear stress. What is the way to calculate, what method did you use to calculate the shear stress within the contact area?
You mean the shape of the raceway?
Shear stress.
Shape is a Gaussian shape.
Yes. What is the way to calculate the shear stress? Shear stress and shear.
We also have the geometry equations, and to find out the contact angles variations of the between the ball and the raceway, and this will this also affects the force calculations.
Mhm. Okay, I think that you did not take into account the stick-slip phenomena in your model. I think so. Okay, thank you. Thank you.
Okay, thank you.